Welcome back, everybody. Our second speaker in this block this morning is the inevitable, inimitable Chris Neugebauer. Indomitable, I'm not sure. Unavoidable, yes. He is here today to speak to us about taking a swim in your kitchen sink while swearing. No? I'll leave it up to him to explain what's going on. Everyone, please welcome Chris Neugebauer to the stage.
Hello. I've never been described as inevitable before. That is quite a long word given the topic of today's talk. Today we're going to be talking a lot about 5-letter words, and I don't know how many letters are in inevitable at the moment. Before I begin, Wordle is owned by the New York Times. I'm not from the New York Times. I will be using their trademark quite a bit during this talk. It's unavoidable given the subject matter. So today we are going to talk about a few things. We're going to talk about Wordle itself. We're going to talk a bit about concurrency in Python and where things are at with that, and also some things that are related to either Wordle and or concurrency. So I play Wordle most days. Everyone else play Wordle? Wait, who here is just here to watch me speak? Who's here for concurrency stuff? Okay, right. So all the people who are here for either of the two things in the middle will be slightly disappointed. Some mediocre talk about Wordle, a mediocre talk about concurrency. Hopefully the two things together will be interesting. I play Wordle most days. I play in hard mode. I'm comfortably average at it. I usually take 3 or 4 guesses. Here's a picture from me playing on Wednesday where I managed to get it in 2, so I'm just making myself look better than I am. My starting word these days is tears, which I know for a fact is not a possible answer in Wordle. As you'll see later, it's what my solver thinks is the best possible starting word, and who am I to argue with code that I've written? My old starting word was irate. If you play Wordle, you'll know that that was an answer within the last month, which is really disappointing because I'd started using the word tears by then. Anyway, there's no actual spoilers in this talk. I wrote most of the slides earlier this week. I might have looked at Wordlebot around then. I wrote all the slides before I knew what today's word was, and I've already forgotten what today's word was. And also, I think it's important to mention this talk probably won't change how you approach Wordle as a human being, which I believe most of you are, Benno. Yeah, exactly. I'd hate to spoil your enjoyment of a thing that's generally quite a pleasant thing that some of us derive some level of enjoyment from. So I don't think Wordle, solving Wordle as a human resembles solving Wordle like a computer would, because we're really not good as human beings at reasoning about a large amount of data in our heads. And what do I mean by a large amount of data? Well, according to the yet another word list that a number of word games use, there's 12,036-ish English language 5-letter words. The solver that I use uses this word list. And even if you filter out obvious plurals, which Wordle itself does for its answer list, there's still in excess of 8,000-ish words. It's really hard to keep that many words in your brain and reason about that sort of problem space. Now, even after you make a good first guess, which most people will have a good first guess, there's normally somewhere between 60 and 500 words left in the problem space to make your last 5 guesses with. And even with that in mind, it's really difficult to memorize which 60 to 500 words are going to be left in the list, because every word will split that set of English language words differently. And so the way that most people go about solving Wordle is to basically just do what everyone else does. And just to give you an idea of how well we can see how everyone else plays at Wordle, the New York Times, sometime after they bought out the game, they started collecting statistics because they're a tech company, and they collected statistics, and they made a site called WordleBot, which is both a Wordle solver itself, but also a site that will give you player statistics for playing Wordle. And if you check in on WordleBot, you get some interesting information, particularly if you're an Australian person or somewhere on this side of the international date line, you can join in on WordleBot basically the moment people have started playing. This is a screen grab from WordleBot on Wednesday morning here in Australia. I took it at 6 a.m., a dedication to preparing slides. And so really you've only got the early risers and people from New Zealand here included in the stats. And you can see that most people who play Wordle earlier in that 48-hour time window, they pick adieu as their first word. Why do people pick adieu as their first word? It's because it's got a lot of vowels in it, and people think that figuring out which vowels will help them solve Wordle quickly. And this was sort of a strategy that people latched onto very, very early in the days of Wordle. If you take a screen grab at 6 a.m. My time, I live in California at the moment, so I play Wordle 17 hours later in California than I would in Australia, and you can see that the most popular word is least. Adieu is still up there, it's number 2. But what do you think has changed between those 17 hours? Okay, you've got everybody who subscribes to the New York Times, which nobody does in Australia, who've looked at WordleBot and know that least is a better word than adieu because the New York Times says so and they use it as their starting word. The New York Times actually no longer says that. They say slate is the best starting word, and that's now number 3. And so once you make your first guess, generally it's really just down to remembering a few good second guesses, remembering some patterns. And then the further you get into the game, it's really just down to how much you can make educated guesses about what the answer is. So yeah, we really don't have the mental capacity to play Wordle like a computer at all. Wordle can play a lot closer to optimally. Wordle is a guessing game, and the way to play a guessing game is to make a guess that we think will reveal the most information about a solution space to a problem. And thankfully, information is a formal term, and we can use that formal term to figure out how to build a solver for Wordle. But I'm not going to build a solver for Wordle. Firstly, I'm going to discuss a simpler game to play, which is the guessing game, where you have to guess a number between 1 and 1,000. And the game will tell you if the answer is higher or lower. So what's our first guess? Right, you guess the number in the middle, and then immediately the solution space gets halved, and then you can guess the middle of that space, and you halve the solution every single time. And with this game, you can play optimally, and you know, like, unless you accidentally happen on one of those answers, you will know exactly how many guesses it will take you to get to the correct answer. So back to this idea of information. Every time you halve the solution space, the base 2 log of the size of the solution space reduces by about 1. If there were 1,024 spaces, it would reduce by 1 every single time. So we describe this halving of the solution space as gaining 1 bit of information. So the idea of expected information gain is that the base 2 log of the solution space less the expected base 2 log of the solution space after a guess is your expected information gain. So for our guessing game, that expected information gain is always going to be basically 1 bit. So what about Wordle? We can sort of apply these theories to Wordle, but the difference is with Wordle, you can't actually play optimally. You can't be guaranteed to play optimally. The same guess is going to reveal different amounts of information depending on what the actual answer is. So the best thing that you can do is make an estimate. And so we can also figure out how good our estimate needs to be. We can see that the solution space for the set of 5-letter words in the English language is about 14 bits. And that means that we need to reveal about 2.33 bits of information per guess, which means somewhere between splitting the solution space into a quarter to an eighth. Somewhere in that sort of space you need to do each guess in order to guess the solution in 6 guesses or less. So back to my starting word. Here is a worked example from a few weeks ago. I took my solving codes, preferred first word, and I got a green T and a yellow A. So if I guess the word today, depending on the information revealed to me, I might end up with 3 potential answers, or I might end up with only 1 potential solution remaining. So that's 13 potential answers in that solution space. It gets split up into 7 groups, and so the expected number of solutions I have after the guess is going to be 1.86 words. And that's a gain of 2.81 bits of information, which is better than the 2.33 we need. On the other hand, if I had guessed the word Titan, I'll still end up with either 3 words or 1 word remaining, but there's far more ways for me to end up with just 1 word than 3. And so that's 13 words split up into 9 groups, which means I have an expected number of solutions of 1.44, which is a gain of 3.17 bits of information. So that gives us a strategy for playing Wordle. The idea is to pick the word with the smallest expected solution space size, make a guess with that word, and then eliminate all those words from the set of answers, and repeat that and repeat that and repeat that until only 1 word remains. So let's look at some Python code. This is a Python conference after all. Here's what the main loop of my Wordle solver looks like. We make a guess, and then we classify the guess that we've made against the actual target word, and then we filter the solution space against the classification that we get. Just as an aside, I structure a lot of my code like this, with a high-level top-level function that can be split out into easily testable functions. Only one of these things is going to be subjected to concurrency later on, which is handy. So let's take a look at the second of those 2 steps. This is a classification routine. I'm using an enum to describe whether the letter is in the solution or not. Enums are great. You should use them. It says whether the letter is yellow or green, and then it just returns a 5-tuple of these classification objects, which can then be used as keys in a dictionary. You'll see why why these should be used as keys in a dictionary. That's important kind of later on, which is it here? No, it's not. Here's the implementation of the filtering function. It takes those classification 5 tuples, and it runs them against every word in the solution space, and it returns only the words in the solution space that match the classification. I've written this solver 3 times, and every single time I've written a for else block here. I've had the opportunity to decide not to do that, and it's always been the right idea as far as the code I've written. Sometimes it's justifiable. So here's the point where we actually make a guess. So the first function that we're going to try to do to make guesses is just to loop through the space of possible guesses, find the potential guess with the lowest potential score, which is the number of groups of words, also the average number of answers in each group. There's no tie-break facility here, which means it might not always make an ideal guess. You'll see the effect of that later on. And then the scoring function, there's another for loop in that. We go through every potential answer, classify our guess as if the potential answer is the actual answer, and then see how that guess would split the solution space. So the more groups, the smaller the solution space is likely to be after the guess, and we just average that for every potential answer. So I guess the first question is, does this approach actually work well? Does this solve the problem that we have? So I'm using the target word snake, and you can see that it solves the Wordle in easy mode in 5 guesses. A lot of these words are really, really obscure and probably not ones that I would guess personally. Spalled means to splinter or chip. Before I move on, there's one code simplification that I suggest using. This is what my actual code does. Here's our make guess function. It's a lot of Python code. It can be rewritten like this, which has the nice effect of running the outer loop in C code. It makes things somewhat, but not importantly, faster. So there we go. We can solve Wordle in about 3 minutes on my M1 MacBook here. So can we do better in Python? So the first place you might start is looking at thread pools. Threads are chains of execution that exist within the same process segment on your system. Here is our make guess function, and again we have this loop, and we do exactly the same thing every single time without modifying any data structures. And then the inside of that loop is also quite resource intensive. There's 2 nested for loops. So there's that, and so we can pull this out. And this is where the concurrent futures library comes in Python. It is often my first port of call for any sort of asynchronous programming, even before using async await. I find it somewhat easier to conceptually put things together that way. Your mileage may vary. It's definitely much easier than writing raw threads in Python if you have a problem that's amenable to threading. So you can think in terms of calling functions and waiting for a result rather than working with things like locks, which I think are a bit tedious and prone to getting those things wrong. So here's what our make-guess function looks like with a thread pool. We submit each potential guess to the thread pool, which returns a future, which is an object that will eventually hold the result of the guess that we made. And then we're going to associate that future with the word that we used to submit it so we can actually get a score back and know which word it was that generated the best result. We're still using that min built in that I used in that code improvement. We grab each result as it comes out of the thread pool complete, and we do that by using the as completed function, which is in the concurrent futures library. So we can set up a thread pool with 8 workers. I have only 8 cores in my machine, so we won't get more than an 8 times speed up. And we can go from our looping code, which takes 185 seconds to make its first guess. Wehrme, by the way, a Westphalian vigilante society. And here's our threaded code, which takes 181 seconds to make a guess. Why? The GIL, yeah. So this is where I point out that Python has a global interpreter lock. The global interpreter lock is it's a lock. It prevents multiple threads from having access to any piece of state that is held by the Python interpreter. In practice, this means that only one Python thread can execute at once. I think it's actually quite interesting to note here that the GIL basically prevents concurrency, but it's very, very, very efficient at preventing concurrency. We don't actually get any slowdown from various threads having to acquire and release the GIL here. It runs in basically exactly the same amount of time. It's like 5 seconds difference. That difference is down to me running Chrome on my computer at the same time. Don't do that if you're trying to do scientific analysis of your speed up. That's a really bad idea. So are threads useful in Python with the GIL? Yes, if you have parallel code that's not written in Python and you can release the GIL on each thread. If your parallel code is I/O bound, but only up to a certain amount, only to a certain extent, async is much better for that. If you can run your code on PyPy and things will be better, it's really not good for writing a Wordle solver. So the next thing we can try is a thing called process pools. So processes are spaces of execution that are managed by your operating system, and they have their own memory. They don't share memory between multiple processes. In practice, it's really only possible to communicate between processes over things like sockets or files, or specially declared shared memory that your operating system manages for you. The good news about processes is that there's one GIL per Python process. So if you have multiple processes, you only have one GIL per process, and you should actually see some speed up. And if you're using the concurrent futures library, the only real difference between using threads and processes is defining what sort of pool you use. So I'm using a process pool executor instead of a thread pool executor. And to remind you, our single-threaded code took 185 seconds to make a guess. With process pool executor, it took 38 seconds, which is actually a speed up, which is cool. It's about 4.8 times. So what if we wanted to see if we can get more speed up? Well, we can change this max workers parameter to 8, from 8 to 16, and it goes from 38 seconds under 8 workers to more than 38 seconds. This again is because I have only 8 cores on my laptop. So my laptop only has 8 cores, which is obviously the maximum speed up I can get. 16 processors can't run on 8 cores at once, but I only got 4.8 times speed up with switching to a process pool. This is where I go into our undergraduate computer science curriculum and talk about Amdahl's law. If you know about that, you can check it off now. But for everyone else, the quick explanation is that a programming task can be split into parts. The Wordle solver has 3. You can score every word. You need to do that. You need to find the minimum by looking at every single word, and then you need to filter the list of solutions. The scoring task can be split up into chunks, and you can run all those bits in parallel. The bits that run in sequence cannot be run in parallel because they run in sequence, and that establishes a limit on the amount our program can be sped up. But also, in reality, there's a bunch of work the operating system needs to do in order to coordinate all these processes to deal with shared memory, those sorts of things. That gets added into our execution time, and that coordination actually increases as we start to add more processes beyond the number of cores that we have on our system, and that's where that extra slowdown came on. So maybe there are other bits that we can run in parallel. Maybe we can run the filtering operation. It turns out that really just doesn't do much. It actually, in fact, slightly slows down things because there's not a whole lot of, well, there's actually too much inter-process communication going on in that filter operation. So to get a task from one process to another, it actually has to be explicitly communicated. And that takes time. That's this sort of OS coordination thing I showed in that diagram earlier. Processes, they work best, process pools work best if you can have longer running tasks that don't need to communicate very often. And that gives us another insight into how to make things a bit faster. So instead of submitting thousands of relatively small tasks into the process pool, if we spend some time actually breaking up our problem space into as many cores that we have and running those sequentially, we can solve the problem locally within each chunk of the problem space and then find the global solution afterwards. So we're actually just making use of the make guess with loop function that we wrote earlier, and we're only doing 16 pieces of inter-process communication instead of the 24,000 pieces of inter-process communication that we were doing with the obvious way of chunking things up. And so here's our version without chunking up the inputs. This is the one with lots of inter-process communication because we're submitting small tasks, 24,000 small tasks into 12,000 small tasks into the process pool. It takes that long. Here's the version where we're only doing 8 submissions into the process pool. You'll also notice that the opening word is different. This is because our tie-breaking behavior is not really deterministic. It really depends on what thing comes first out of the process pool. So instead of tears, we have hairs. It is faster by a noticeable margin. Spalt, by the way, it means brittle. So process pools, they are good if you have a small number of large but CPU-bounded tasks. It takes a lot more work to set these up efficiently. You need to think about how you split your problem space up such that you reduce the amount of inter-process communication you have. This is different to how you would deal with threads in a language like C or Java. And it's reasonably good for writing a Wordle solver. I included the word async in the title of the talk. That's only because I needed a third 5-letter word that was relevant to concurrency. It has the same problem as thread pools in that everything runs within the same process space as Python. So you'd always end up with something related to the GIL if you had a different event loop that did allow for thread-based concurrency. If you dealt with process-based concurrency, well, you're dealing with a whole lot of language-level complication that would make things slower. Finally, let's talk about NoGIL, because as I mentioned, Python has a GIL. It's always had a GIL, and people have always wanted the GIL to go away because it gets in the way of using threads efficiently. There is a new effort called NoGIL, which is about the 5th effort that I've seen in the last 10 years, and it seems to be making some level of progress. In terms of making, using concurrency in Python without the GIL actually usable. You can install NoGIL very easily if you have pyenv on your machine. Just go pyenv install NoGIL 3.9.10-1. It is only supported in Python 3.9. This is important because in Python 3.11, there's a team at Microsoft running the faster CPython project, and the faster CPython project did a lot of work to make CPython faster, and they actually succeeded, and all their work landed in Python 3.11. So our first guess in Python 3.9 under NoGIL in a single-threaded sort of context took about 40 seconds longer to run than it did in Python 3.11. So our first useful lesson, if you need to make your code faster and you're still running Python 3.10 or earlier, upgrade to Python 3.11, it will get faster. For free, basically. What takes even longer than running our single-threaded version in NoGIL is running it with a thread pool executor. So instead of taking about the same amount of time as a single-threaded version as it took in the GIL, with the GIL, it now takes about 1.6 times longer than it did in a single-threaded execution. As I was mentioning earlier, the GIL is actually really, really, really efficient, and this is why all these GIL removal projects have sort of faltered over the years. There's not really any slowdown from acquiring and releasing the GIL in normal Python. On the other hand, once you start adding a lot more locks and things like finely grained thread safety into the memory allocator in Python, things get really, really slow. 1.6 times slower, as it turns out. You may be asking whether or not NoGIL is worth it from this one example I've given you. First up, slowing down only 1.6 times is a huge improvement on previous versions of trying to remove the GIL, especially since the authors actually have an idea of how to make this get even faster. Secondly, there are actually demos on the NoGIL README that demonstrates a CPU-bound function that parallelizes basically with the number of cores you have and the number of threads you give it. It's a really contrived example. It doesn't touch any data structures, but it demonstrates that you can run threaded Python code in ACPython and get unbounded speed up, which is very impressive. There is a PEP to remove the GIL. There is a guarantee of sponsorship to do the real work to make it faster. I would not be surprised if the GIL goes away in the next 3 to 5 years. And that would be really incredible. So to finish up, we've finished talking about concurrency in Python. Let's get back to talking about Wordle, which is what I'm actually interested in. Firstly, all the examples I've shown you have been in easy mode. I play in hard mode. It's probably interesting to see what it would take to make the solver work in hard mode. It's really just a matter of changing one line at the bottom of the main loop. Very small. So we're now, instead of guessing with the entire set of English language words, we're just solving with the set of answers that we get after each step. And it very slightly changes the guesses it makes. It significantly reduces the amount of time the subsequent guesses beyond the first takes. That's because there's fewer words to choose from. It takes less time to run. CPAL is the parts of the calyx of a flower. And finally, how good is this solver at actual Wordle? Before the New York Times took over, the full set of answers to Wordle was visible in the JavaScript source of the game. So you could basically strip that out and use it as an answer list. There are copies of this all over the internet because it's the internet. There's about 2,300 words in that answer list, and we can run our solver against all of them. Firstly, to establish a baseline, let's see what the behavior is like if we just guess randomly from the set of all possible solutions. It solves the game correctly in about 90% of the time, and there are 3 words that trigger a bug. I think this is just due to there not being an answer in the guess list, and I haven't just done enough error correction in the code to account for it properly. Code for us talk. In easy mode, there's those 3 bug cases that we saw in the random guessing thing. It successfully solves all but one puzzle in 6 guesses or less, and it does well in more than half of the words in 4 guesses. So I basically play about as well as my solver does personally, which is cool. The one word that it can't guess is Joker. It takes 7 guesses via a bunch of really quite obscure words, including afflage, which is a type of irrigation system originating in Oman. We can run the same exhaustive solver in hard mode as well, and it fails to solve in hard mode a lot more than in easy mode, which you've probably experienced if you play in hard mode yourself. There's a lot of cases where you accidentally get locked into a sequence of equally likely answers, where an impossible answer might split up the options. So for example, this word curvy here, if you could guess the word vens on the 3rd guess, you would guarantee a solution for those curvy, kerny, curdy, or you get a choice between curly and curry. So you get 1 or 2 guesses. You can't use vens in hard mode because it's already said that S and E aren't in the solution, so you can't use that. And so we fail to solve in about 91 cases now. There are 4 words that are unless, again, bugs, I don't know. Unsure what's going on there. It manages to solve about 96% of cases in hard mode. Finally, one small optimization you can make to the word list, which is to remove plurals. The NYT removes words that end in S or ES if they're plurals or transitive verbs. It changes the opening guess from tears to pert, which means lively. And we now solve in 97.5% of cases, but now there's 7 words where the answers aren't in the guessed list. So to recap, it's reasonably easy to make a good Wordle solver. It was a fun exercise. I encourage you to do it, or you can copy my code, whichever you prefer. Threads aren't great for Wordle-style problems, but process pools are. My sources, yet another word list, which you can download to make your own word games. The original version of Wordle by Josh Wardle for the actual answers list. The introduction to the Wordlebot algorithm from the New York Times that explain how all of that works. And if you want to read my own code and poke holes at it, it's available on my GitHub. Thanks, everyone.